One important part about drug development in medicinal chemistry is that this wonder drug, you can have a wonder drug, it can cure cancer, it can do fine in tests, but it has to dissolve in the body in order to be effective. Because the human body is mostly water, and so any wonder drug developed has to dissolve in water. So the process of dissolving in water is solubility, and functional groups play an important role in the solubility of a compound or the solubility of a drug. So here's the water molecule, and remember, water is a polar molecule because it has polar bonds on the bent shape, so there's an uneven distribution of electrons leading to a positive side of the molecule and a negative side of the molecule. Now, the interesting thing about the OH bond, so the OH bond is a polar bond, and that polar bond has a polarity where there's a negative end and a positive end. Methanol is an example of this CH3. This is nonpolar, but just having a polar portion, just having the OH group attached to CH3 allows for this molecule now to be soluble in water because it has that polar bond with the partial positive and partial negative on there. This can attract to water molecules and then be surrounded by water molecules and be soluble in water. This is another example of a polar molecule that has a nonpolar end. So the CH3 group, this is all nonpolar, and this will not dissolve in water. This end of the molecule, this is the carboxylic acid end, it's COOH. This has the polar bond, the OH group has the partial negative and partial positive, which will then attract to water molecules, which can then surround this entire part of this acetic acid, and then this makes acetic acid dissolve in water. So you only have to have a portion of the molecule that's polar, or a portion of it will allow for the entire molecule to be soluble. A functional group added, like an alcohol group, or another example is the amine group. Adding an amine group will also add a polar bond and impart polarity, will make your whole molecule polar and soluble in water. So, and that's because those bonds, OH or NH, are polar bonds, and they have the dipoles with the partial negative and partial positive that can attract to water molecules. The solubility of vitamins has dramatic and important consequences for your recommended daily dose. That's on the nutrition label. So there are vitamins that are water soluble and fat soluble. So the vitamins that are water soluble have polar bonds in them. So this is an example of the structure of vitamin C. You can see all of these OHs, these are all alcohol groups. There's also an ether group and a ketone group here. These OHs, these alcohol groups, are polar, and so this vitamin C is a polar molecule overall. This polar molecule will then attract to water molecules, and that's why it's called water soluble. So vitamin B is also water soluble. The water-soluble vitamins that have polar portions, well, these, your body will flush out any excess because it's water-soluble, and so you need daily amounts of vitamin B and vitamin C. They do not store in your body. So the example is vitamin B12 you can easily become low on, and so it's popular to get a vitamin B12 shot. Vitamin B and vitamin C can come from foods or can come from vitamins or from shots, but that you can become vitamin B deficient or vitamin C deficient. A vitamin C deficiency results in a disease called scurvy, which was discovered as people sailed from the old world to the new world and did not get enough regular amounts of vitamin C. These are the class of vitamins that are called fat-soluble. So fat-soluble are vitamins A, D, E, and K. And here's the structure of vitamin A. So vitamin A is mostly nonpolar, which is hydrocarbons. So a bunch of carbons and hydrogens on this side of the molecule. All of this side of the molecule. There's only one little part that this is the alcohol. So this overall is a nonpolar molecule that is not going to dissolve in water, but can be stored in fat in the body. So these vitamins A, D, E, and K are stored and collected, and so you don't need these daily. So water will dissolve polar compounds and ionic compounds, but not nonpolar compounds like vitamins A, D, E, and K. Most drugs are also organic compounds that are mostly hydrocarbons, so drugs are generally not water soluble. So adding a functional group like an alcohol group or an amine group will make your drug soluble. Another thing that's done is formation of a salt. Salt, remember, is an ionic compound in general. So having an ionic end, similar to the soap molecule, this is a reaction that's done to form a salt from your drug. So this is pseudoephedrine. Well, a reaction with HCl forms this molecule that has the nonpolar end. So there's this benzene ring, and then this ionic end. Here's a positive charge and negative charge. Having the ionic end allows for this to be attracted to water molecules with the partial positive and partial negative ends on the water molecule. Now there are other benefits of having the salt, the ionic end of a drug. This is not just solubility, but it also improves shelf life, reduces odor, and stability of the drug. Is in the final marketed product of pseudoephedrine, and it's actually in the name hydrochloride, which means that it has the HCl, the ionic end, attached to the drug that allows for this solubility.